Hey, fellow mathers! Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam-packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over $6,000 worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show. Are your notifications off?
Yes, they are, but I'm ready to start because it's recording.
Bye.
You ready? Okay, here we go. Hey, fellow mathers, welcome to the podcast where math is figure-outable. I'm Pam Harris, a former a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figureoutable, we are on a mission to improve math teaching.
We know that algorithms are amazing historic achievements, but they're not good teaching tools because mimicking step-by-step procedures can actually trap students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing, building relationships with your students, and grappling with mathematical relationships.
And we invite you to join us to make math more figure-outable. Kim, that second sentence is really long in this new introduction.
It is. We might have to alter it.
Yeah, listeners, you can tell we're only on episode 202, and so this is a new introduction that we've talked about. But boy, I might have to break up that second sentence. I had to take a breath in the middle of that sentence there.
Well, I'm glad you were talking because I coughed a couple of times. Thank you, Craig.
Because it's allergy season. Oh, man.
I apologize.
Yeah, listeners. So thanks for joining us while we're both gagging. Just a slight bit on all the drainage here. If you don't have allergies, you will within 3 years of moving to Central Texas. So welcome to our delightful. Yeah. All right.
Okay. Let's get started.
There we go.
So I knew that we were going to talk a little bit of high school today. So I actually went looking for a comment. You know, I'm loving reading the ratings and reviews.
Oh my gosh, we love reading.
So happy. Okay, so check this out. You haven't heard this. Love M314 says awesome ideas. I've taught for 33 years and have many times been frustrated with the lack of numeracy foundation in high school students. Yes. I Have You Need is a great place to start.
Nice.
So anywho, yeah. Nice pi reference in the name.
There you go, 314.
And we agree that numeracy is something that we need to build in all students. And at the high school level, you see the effect of years and years and years of rote memory. Mm-hmm. I Have You Need is a super routine for all ages. And we have something to talk about today that's aimed at helping math in high school more figure-outable. Maybe some new ways to think about I Have You Need too.
Let's do it.
Yeah. So if it's been a minute and you are not a high school teacher, you might have sweat just a little bit seeing the title of this week's episode, but take a deep breath. We're not going to leave you astray, and you can learn right alongside me. I don't even know what's happening today.
Bam. Yeah. All right. So I plan today, and I think this is going to be a lot of fun.
Yeah.
One of the funnest, most rewarding things I do is do workshops where I have kindergarten through 12th grade teachers in the room. And we do something where the first grade teacher goes, Hey, I just reasoned through that. I just used what I know. And the high school teacher goes, well, wow. All right. This is figure-outable. So it's a nice thing. So here we go. Let's figure out some high school math.
Okay.
Kim, do you relate more to snowboarding or skateboarding or maybe even trick bike riding?
Neither, except I'm planning to go skiing or snowboarding. I'm going to try that ski this year, but I'm going to try snowboarding. So let's go with that. Maybe I'll get into
Well,
mode.
so you can picture snowboarding,
Oh
huh?
yeah, for sure. I lived in Alaska. I know snowboarding.
Well, bam. Okay, so picture any one of those: skateboarding, snowboarding,
Okay.
some bike riding. And if I said, "All right, they're on the course and they just," see, now I don't even know the lingo, but they spun a 360.
Yeah.
What would be happening if they spun a 360?
Oh, they turned all the way around.
Like, keep going. Like, what? Like, can
Yeah.
you describe that some more? Like, turn all the way around.
So they made a
So
full circle.
full circle. Like, if
Yeah.
they're facing one direction and they spun a 360, they're now facing that same direction, but they went all
Yep.
the way around.
Yep.
Yep. What if
hmm
they spun a 180? What would that look like?
They went halfway around the circle, so they're facing the opposite direction.
Bam. Okay, so 180, I'm going one direction. If I spin that 180, I'm now the opposite direction. I like I'm backwards
hmm
almost, kind
hmm
of. Okay, cool. So we could use some intuition about these angles that kids have kind of learned. Like if I were to say, look around right now and find a right angle. What might be something, I don't know, handy that you have, Kim, that you would be like, that's a right angle. Anything
Oh, on the
handy?
corner of my paper.
Yeah, you get a paper. Yeah.
Yep.
In fact, sometimes in geometry, we would say, "Hey, pull out your right angle checker," and kids would go, "What?" And you're like, the piece of paper you're holding right there. That corner, right? The corner is
Yep.
sort of 90. And how does that corner relate to that 180 that we just spun?
So the corner is 90 degrees, and so it's a fourth of the circle
Of the whole
of
circle,
the angles.
of the 360, and
Yep.
how does it relate to 180?
Half.
Just like half of that. So
Yep.
if we spun that 180 and we're now backwards, like we've kind of turned backwards. If
Uh-huh.
we only spun 90, we'd kind of just turn a quarter circle. Yeah.
Yep. Yep.
Okay, cool. So let's think for a second about that 360. If we kind of trace the path that we traveled, we could sort of, I think you even said a circle, right? We could think about kind of the whole circle. We start here, we spin all the way around. If we talked about walking that circle, like if an ant kind of walked around that circle, then that would be the circumference of the circle. We name that distance around the circle. If I were to measure it, kind of like put a piece of yarn or string around the circle, and then I were to pick up that yarn or string and I would lay it along a ruler, I could measure the circumference of that circle. That would be kind of how far I'd have to walk around. Like if an ant was walking around that circle, it'd be kind of how far that ant would have to walk around, right? That
hmm
we
hmm
call that the circumference. So one of the things that I'm not going to develop today is the formula or how you could find the circumference if you were given the radius of a circle.
hmm
So I'm just going to tell you today just for fun. So you could find the circumference of a circle by multiplying 2 pi times that radius. So if you knew the radius of the circle, then you could multiply by 2 pi. I'm not going to develop that today. We could do that some other time. But so if I were doing today's lesson, I would expect that students had some experience with 2 pi times r times the radius to find the circumference of a circle. Are we good?
hmm hmm
Okay,
hmm
cool. So what if everybody just picture that circle that I'm kind of talking about, and you're kind of thinking about an ant starts in one place and he's kind of walking around that circle. And so depending on how long the radius is, the ant would have a shorter distance to walk or a longer distance to walk, because like a tiny circle is going to have a short circumference, right? And a
hmm
big huge circle is going to have a long radius. The ant's going to have to walk around that whole circle, and that's a sort of a long circumference. Well, what if I said today the radius of that circle is 1? And sometimes we call 1 a unit, and so I might call this a unit circle just because like the radius is 1.
Okay.
So if the radius is 1, how far does the ant have to walk?
If the radius is 1,
Yeah, the radius of the circle is 1. How
it's going all
far?
the way around.
All the way around. Yep. How you doing there, Kim?
Yeah, I don't know.
So, okay, what are you thinking? Can you share what's going on in your head?
I mean, I feel like did you tell me anything other than it's 360 in a circle?
The circumference we could find by multiplying 2 pi times the radius.
Oh, sorry.
That would be another thing. That'd be another thing that we.
I was like, wait, I feel like I don't. Okay, so 2 pi.
Yep. So why is it 2 pi?
Because it's 2 pi times the radius.
You're doing
The
great. You're
radius
doing
is
great.
1.
All right, the radius is 1. Okay, so the circumference for if it's a unit circle, if the
Yeah, yeah.
radius is 1, then the ant has to walk 2 pi, and pi is about. Hey, we just said that in the it's about 3.14. So what 2 pi would be about?
Uh,
Pi's 3. How you doing, Kim?
Yeah, yeah. So the so
Pi's about 3.14, and
yeah,
so
yeah.
2
So
pi
it's like six something, 6.28.
6.2, 6 something, or about 6.28. There we go. Okay.
Yeah.
So the poor ant would, like, be walking for a hot minute at
Yep.
6.28, whatever the units we're measuring in,
Hmm.
about 6.28 units around the circle. Okay, so interesting that there was some work done in mathematics where people began to realize that there were these periodic things that happened. And one of the ways that they could kind of conceive of modeling these periodic things was to kind of let the skateboarder, or you're going to go snowboarding, the snowboarder keep spinning. What do I mean by that? I mean, like, if you were to start facing one direction, right? And you just said that if you were to spin a 360, then you'd spin all the way around. Well, that's kind of the circle. And so you could picture that. You could be like, okay, I'm going to spin all the way around and I'm back to where I began. But what if I keep spinning? Well, I wouldn't call that. I mean, I could call it two 360s unless I kind of did it all at once, right? Like if I literally spun all the way around and kept spinning, then I could say, well, I've spun more than 360. And they realized as they started seeing periodic things happening, for example, sound waves, we can model that they're periodic. They do something over and over and over again. The sun rises and sets in a periodic fashion. It rises and it sets, and then it rises and then it sets, and then it rises. And temperature goes up and it goes down, and it goes up and it goes down. And we can actually track temperature over time. And if we were to plot temperature over time, we could see this sort of wavy thing happening. And we call that kind of this periodic behavior. And mathematicians wanted to model that periodic behavior. And they realized that it would be super helpful if they were able to let the angle measure, as they're sort of noticing how many times you're kind of spinning around that circle, that if they let it be the distance that turtle, I don't know, I said turtle, I was saying ant earlier, whatever's walking around the circle, if we let that ant walk around the circle, we can actually kind of equate the angle measure with how far the ant walked. I don't know if that makes any sense, but in other
Yeah.
words, if I said, hey, Kim, the ant just walked about 6.28 units,
Hmm.
what angle would that be equated to?
360.
360. So we could say, all right, so sort of this 2 pi, we could kind of say that's if the ant walked 2 pi, we could say that was like the angle of 360. Well, what if the ant only, so if you were, if I, this is the downfall of a audio podcast, y'all, but I literally just drew on my paper a coordinate axis. So I just drew an X axis and a Y axis, and they're crossing each other, like normal. And then I'm going to say that the skateboarder or whatever is sort of facing, God, how do I describe this? On the X axis, it's kind of facing to the right. It's sort of that, like between the first quadrant and the fourth quadrant. This is
Hmm.
hard to describe. So if you kind of, if the ant is kind of sitting on that first quadrant, and let's say I drew a circle and the ant's going to walk around that circle. Right now, my ant is this is a unit circle, right? So it's at the point 1, 0. Like, can you find the 0.10?
Hmm.
Okay. So if the 1, 0, I'm over 1, I'm not up or down, I'm just like sitting on that axis. The ant is sitting there. And you just said if the ant walked all the way around the circle, then you're saying I would have spun a 360. I just kind of
Hmm.
repeated what you said.
Yeah.
Okay. So I just wanted to let you know what's on my paper. What's on my paper is a circle that is centered around the origin. And I've got that 0.10, and I've drawn that circle from that point all the way around. And if I go all the way around, that's either walking a distance of 2 pi or it's an angle of 360.
Okay.
Yeah? Okay, cool. So the mathematician said, we could just kind of equate those. We're just going to say that the radius is 1. And so instead of saying the ant walks around 2 pi, we're going to say that the angle measure, that angle measure of going all the way around and ending up back where you were, walking all the way around 2 pi, we're just going to call them kind of the same. We're going to equate. We're going to say the angle measure is either 360, or we're going to also say it's 2 pi. So we're
Okay.
now kind of talking about an angle measure. Cool. So what if that ant only walked halfway around the circle? What if it only walked pi around the circle, about 3.14 of those units? What
Hmm.
angle was that again?
180.
That was 180. So on my paper, I've just drawn like half the circle. I have the circle drawn, but now I've kind of sort of drawn over it as if it's kind of an angle. Like you know how you draw that little angle, like arrow thing? It's kind of
Hmm.
like this, yeah. So I've kind of drawn this angle arrow thing over there, and I'm saying, okay, so that half circle, or sometimes we call that a straight angle. We could call that 180 degrees, like you said, but we could also call that pi, because you just said, like, how do you know it's pi, by the way? Did
I
I
think
say it was?
you told me it
Did
was
I tell
pi.
you it was pi? Well,
Hmm.
shoot, I wish I would have done the other. What if you've gone that 180 degrees? Is there a way that you could reason it was pi without me telling you it was pi?
Yeah, it was halfway around the circle. And if the whole circle is 2 pi, then 1 pi is halfway around.
Halfway around. Okay, that totally makes sense. What if we only did that 90 degrees? So now I'm kind of drawing just a little loop that goes sort of up to the y-axis. It's kind of that 90 degree. What
Hmm.
would that be in terms of pi?
1/2 pi.
Because
Because if a whole pi is 180, then half pi would be 90.
nice. And so when I now have on my paper written 2 pi equals 360 degrees,
Hmm.
pi equals 180 degrees, pi divided by 2
Hmm.
equals 90 degrees. And I could have written 1/2 pi or pi divided by 2, either one is 90 degrees. Cool. Let's just keep going. What if I wanted to know a fourth of pi? How many degrees would that be? So now I'm kind of switching a little bit. I was doing
Yeah, that's
degrees
good.
earlier. Now, yeah. Okay. So a fourth of
So
pi. Mm-hmm.
fourth of pi is 45 degrees because
Yeah.
half pi was 90 degrees.
Okay, so if half of pi is 90 degrees, then a fourth of pi would be half of that, and half
Hmm.
of 90 is 45. So
Hmm.
I've just drawn on my paper kind of a 45-degree line from the origin, and I've drawn that little angle symbol, and I've kind of written out to the side that that's a fourth of pi. I've also written on my paper, on the left-hand side, I've got 2 pi equals 360, pi equals 180, half a pi equals 90, and a fourth of pi equals 45. Oh, and each of those numbers had a degree by them, 360 degrees, that little degree symbol. So a fourth of pi was 45 degrees. Cool. Next question. What about 3/4 of pi? Or sometimes we call that 3 pi fourths. I don't know why we do that. So I'm going to call it 3/4 pi.
Hmm.
What's the angle that's associated with 3/4 pi? Any ideas?
Yeah, if fourth of pi was 45 degrees,
Mm-hmm.
then 3 times as much would be 3/4 pi, and that's 135 degrees.
And where would that be if I were to? So let me write that down. 135 degrees. Okay, so 90 I said 90. That's how I was checking your answer. But you actually multiplied 45 times 3 to get 135. I thought
Hmm.
90 and 45. Either way, that would kind of work. Cool.
Yeah.
Where would the ant be on that circle? Like, what would the angle be? What would it look like? This is hard to
Um,
do visually in
yeah, well, I'm not
auditory.
drawing anything, so give me a second.
Ah, because you're probably watching what I was drawing, like, which
Well, I'm
is
not
what
watching, I'm
I
listening to you.
know, but
So,
that's what would have happened in class, right? I
yeah.
I wouldn't have expected students to be drawing anything either. I just would have been drawing it on the board. But
Yeah.
yeah, so
So, okay, so I just drew a circle and I really quickly put 90 degrees is half a pi,
mhm,
and I put pi is 180. So it's going to be between those. So it's going to be
nice.
between, yeah,
But
between half pi and 1 pi.
and between 90 degrees and 180 degrees. So
Yep.
it's kind of that 45-degree angle right there in the second quadrant. Could be a way to talk about that. Cool.
Hmm.
If I was in class, I might say to anybody, did anybody use the pi? And like pi would be too much, right? Because
Hmm.
3/4, we were finding 3/4 of pi.
Hmm.
I might ask, did it could you think, Kim, about like using pi to find 3/4? Because you used a fourth of pi and you scaled that up times 3.
Yeah.
Brilliant, brilliant.
Yeah.
Love that, love that. But I'm wondering if you could use pi also to get to 3/4 of pi.
Yeah. I could do pi was 180, but I want to go back a fourth because I only need 3/4 of pi.
Nice.
So back 45 degrees.
From that 180, and that was also 135. Cool, nice. All right, good. Let's get it even a little bit weirder. What about 7/4 of pi? Where would that be, and how many degrees? You could do either in either order. Degrees first, where it is.
I'm going to go back from the 360 because 2 pi would be 8/4 pi,
Nice.
and that's 360. So I'm going to go back a fourth, which we said was 45 degrees. So
Yeah.
that's 315 degrees.
So did you think about when you said 45, you took a deep breath, 45 degrees, you subtracted that from the 360. 360
Hmm.
minus 45 is a 315. Cool. And where I'm sorry, did you already say where it was?
I did not. It's between, so around my circle,
Mm-hmm.
um, like on a clock, the 9 o'clock would be 270 degrees.
The 9 o'clock.
Like on, if I've drawn a circle, I didn't draw it on a coordinate grid. So I drew a circle on my paper,
Okay.
and 6 o'clock would be 180. I'm just trying to give you a visual for where I am.
Uh,
9 o'clock would be 270.
yeah.
So I'm like between 9 o'clock and 12 o'clock,
And so, you know
3:15.
what? Assuming that you could see my paper, what I didn't tell you was I need your angles to all start at 3 o'clock. How weird is that?
Oh, okay. My 360's at the
Yeah.
top. Okay.
Yeah. Do you
You
mind
no wonder you
redrawing?
were confused.
I mean, I followed you, but yeah. So standard position
Mm-hmm.
is that the angles all start. If we're looking at a clock, they start at 3 o'clock. That's where sort of a zero
Oh,
angle
so
would be.
I'm gonna rotate.
Yeah, if you don't mind. So
Oh
let me
gosh.
actually walk everybody listening, because sorry everyone. I should have probably started there. If the ant starts at 3 o'clock, that's the zero angle, and he starts walking, then the 45 degrees would literally kind of be 45 up from that, and so it's going to be, golly, what is that? Pointing at the
One
one
and a
and a
half.
half o'clock,
Yeah.
in between the 1 and 2.
We
That's
call
where
that
the
1:30.
the 1.5 o'clock, the 1:30. That's funny. And then if the ant had gone to a half a pi, then that would be up at the 0 or the 12.
Yeah.
And then if the ant keeps going at the 180 degrees or pi, that would be over at the 9 o'clock.
Mm-hmm.
Okay, cool. So where would you be now if you were at 7/4 of pi?
I just rotated my paper. So it would be at, so if 360 was at the 3 o'clock,
Yep.
then 315 would be, gosh, how do I say this? At the 1.5 o'clock.
Well, not 1.5, right? Wouldn't it be 4.5? Is it the 4:30?
No, if my three, I'm going back to 315 degrees.
Ooh,
Oh, that was your zero. You didn't call that 360 at the 3 o'clock.
I mean, it's both.
Oh, true. That's true. So then 315 would be between what a normal clock would be 12 and 3.
So you're going back.
Right, from 360 to get to 7
Which
fourths pi.
which direction was your ant walking as you were walking around the circle?
From the 3 towards the 12.
Okay, so then when you got to 360, if you keep going up that towards the 2 and the 1,
Uh-huh.
then you're adding degrees. But you've got, from 360, you got to subtract pi fourths to get to 7/4 of pi, right?
Yeah, I think I'm going to need to see your visual because 0 and
Mm-hmm.
360 to me is at the 3 o'clock.
Yep. Yeah. Agreed.
But if that's 360, which is 2 pi, and I want 7 fourths pi,
Do you want less than 2 pi or more than 2 pi?
I want less than 2 pi.
So if we were together, I would be taking my pencil, and I would start at that 3, and it would open up. God, how do you describe that?
Which way
Counterclockwise.
does it open up?
Counterclockwise. So it goes from the 3 up to the.
Okay. See, yeah, that's good to know. It opens up counterclockwise, so then it's going to be below the 360 on a clock. So it's going to be like more like the 4,
For
between
7
4
for
and 5.
7 yeah, for 7
Yeah.
pi fourths. Yeah.
Okay.
Oh, wow. So lots of visual things. I was assuming. So you had your ant walking sort of down and clockwise.
Yeah, my aunt was walking clockwise this whole time.
Gotcha. Yeah, the ant has to walk counterclockwise. That standard position is the ant. The angle opens counterclockwise. Weird,
Okie
right?
dokie. Yeah.
Super weird. Whew. Okay, I don't even know if we should do one more, but let's just try one more.
Okay.
Where would a sixth of pi? What would be the degree measure, and where would a sixth? Again, it's starting at that 0, or 1 0, starting over there at the 3 o'clock,
Mm-hmm.
and it's opening counterclockwise.
Yeah. Okay. So I have to think about this. So I know the degrees. That works for me. So
Well,
if pi
can you
is
tell us? Can you tell us?
pi is 180.
Oh, sorry.
If pi is 180, then a sixth of pi is 30 degrees because it's just a sixth of 180.
Okay, and 180 divided by 6 is 30. So,
Sure.
all right, so pi 6 or
Okay.
1/6 of pi is 30 degrees. Okay.
So if my aunt is walking counterclockwise
Yep.
and I'm at 180, That's pi.
Why are you at 180? Oh, okay.
Because that's where I started.
Why?
Because I used pi to help me figure out a sixth of pi.
Okay. Okay. Thank you.
So I want a sixth of the distance between pi and 2 pi. No?
Well, I don't know. That feels like it would be more than pi, and you only want a sixth of pi.
Oh, because again, in clockwise, so it's going for. So I only want a sixth of the way. Good gravy.
You're doing
So
great.
I'm at the 1 o'clock
Because
it's a sixth of the way between 12 and 6 o'clock on the clock.
12 and 6 o'clock.
There are 6 numbers between 12 and 6.
Ah,
And
okay.
if I'm
Okay.
dividing that pi by 6.
Okay. Okay. But we have to
I don't
start.
know how to describe it other than giving you numbers for location between them. I guess I could have said it's a third of the way between 2 pi and between 0 and, oh, mine's backwards now, 0 and 90. So it's a third of the way between 0 and 90, which would be closer to 0 than it is the middle between the two.
Third of the. Where's your 0 again?
My 0 is at the 3 o'clock on a clock.
Okay. And it's opening counterclockwise from there, right?
Yep. So I'm only going 30 degrees.
Up from that, up
Mhm.
from the x-axis.
Oh, so that's an 11. Good gravy. No. See, I'm trying to figure out the clock and the being at the same time because I've never seen a unit circle.
Yeah. Yeah.
And I don't know which way I'm supposed to go versus.
Yeah. So maybe do this for me. Put your pencil. So draw the axes.
Yep.
Okay. Now draw a circle.
Yep.
And our starting place is going to be at the 3 o'clock or the point 1, 0.
Yep.
Okay. I want you to put your pencil so that the point is at the origin and it's laying on the x-axis.
What
so
point? The 1, 0?
Oh, sorry. The point of your pencil.
Okay.
That was very good. The front of your pencil. The front of your pencil is on the origin and the rest of your pencil is like going to the right.
Okay.
Yeah, I don't know if that. So the way mine looks right, I have the circle, and then I have a pencil laying flat on it horizontally, and it's going from the origin to the right. So
Yep.
it's horizontally. So if I'm going to describe angles, they're all going to start here, and now I'm going to rotate that pencil counterclockwise, leaving the front of my pencil at the origin.
Yes, I'm going to rotate it 30 degrees.
Okay.
So if I were looking at a clock and the 360, the x-axis that you had me start at, then if that's 3 o'clock, then I'm going to be at 2 o'clock.
That's 30 degrees.
Yes.
Up at the 2 o'clock. Because?
Yes. Oh, was I saying 1 o'clock?
Yeah.
Ugh. Okay. Yeah. 2 o'clock. I meant back one number from 3 o'clock.
Oh, back one number. That makes a lot of sense.
Sorry.
Yeah. And I kind of like when you were saying like it makes sense that a movement of a number is 30 degrees because you got 12 of those numbers for the whole 360 degrees.
Yeah.
So each movement of that number is 30 degrees.
Yep.
Awesome. So you sort of, it didn't move very much, right? A 30-degree angle is not very much off of that. It's just kind of 30 degrees. It's one number movement kind of off of that. That would be 30. All right. Kim, we can do it. I only have one more problem. I promise we're done. 11/6 of pi. But again, your pencil has to start on that horizontal 3, pointing at the 3 o'clock.
Okay. So 12/6 is 2 pi.
Yeah.
So that's 360 degrees.
All the way around.
Yep. I need 1/6 less, and that was 30 degrees less. Nice. So that's going to be 330 degrees.
Nice.
So it's going to be 30 degrees less than all the way around the circle.
Cool. And we just decided that 30 degrees was kind of that movement between numbers if we're on a clock. So are we down there at the 4 o'clock?
Yeah. It's one beyond. Yes, because it's going the other direction. See, I'm having a hard time with the counterclockwise, I think.
Yeah, I can see that. And I think, y'all, this is so important. If we were doing this visually, which obviously we would like do that in class, then I would be doing a ton of movement with my arms. I usually like put my arms kind of where I'm telling Kim to put the pencil, and I'm opening up, and it's always going counterclockwise. It starts at that sort of standard position, kind of from the 0 to the 3. And then instead of the clock hands going the way they normally do, they're going backwards. So interesting. I'm not sure I've ever had anybody use the clock to help describe, but it has been helpful visually to kind of describe where we are. But I wonder if it's also getting in the way of hands moving the wrong direction.
I think that's been part of it for me, because I can't see what and this is why modeling is so important.
So important.
Right? Like,
absolutely. Making
teachers are
visible.
Sometimes just saying all the things, and seeing that definitely would have been helpful.
Well, and Kim, I'm really glad that you were helping me become clear about what you were thinking, so that everybody listening could go, oh, okay, like the clock hands are going like normal clock hands. Kim's saying, nope, sorry, with radian measure, the turtle's got to walk the other direction. Like the angles have to open the other way.
Yep.
All right, so let's just end this a little bit by saying, you might be like, why are we doing this thing with pi and angles and all the things? Well, I'll just mention that we needed a real number measure for angles in order to model periodic functions in a very particular way, so that we could do things with sound waves and temperature swings. But then, even more importantly, we added complex numbers, and bam, we get electricity and computer chips. So all of that became necessary. We do need a real number measure for angles in order to sort of do tons of things that came after that. Y'all, maybe the thing that you can take away from this is you don't need to memorize the unit circle. You may have been in a trig class someday when they were like, all right, here's the unit circle. I'm going to give it to you. Memorize all this crazy stuff. Actually, it's all based on relationships. And today we just did sort of the first part of it, talking about how we can find the angles that are in these measures related to pi, but they are all figure outable. Kim, we can actually play I Have You Need with radian measure. I'll be honest with you, it's really a bit more about fractions, but I could say things like, hey, if my total's 2 pi and I've got 1/3 of pi, what do you need to make 2 pi? And should we do that? If I've got 1/3 of pi, but our totals...
Oh gosh, hang on, I'll write something down.
Okay. So if the total's 2 pi, 2 pi, and I've got 1/3 of pi, I probably should have done angle that we already did, but
1 2/3 pi.
You still need 1 2/3 pi left over. Sure. What if go ahead.
But also people can use 360 degrees, right? So
absolutely. Yep.
Kids are having some difficulty with the difference between some of the radians.
Yes. And middle school teachers, when you're doing 5th grade teachers, when you're doing degree measure for angles, you could totally say, hey, if I have 360, if that's the total, and I have 180, what do you need? If I have 90, what do you need? When you're doing complementary angles, you could say, today our total's 90. Bam. When you're doing supplementary angles, you could say, today our total's 180. And you can ask, given the one, what's its partner? So lots of different things that we can do with I Have You Need and angle measure. Kind of fun.
Yeah. If you got nothing else out of today, then maybe I was able to verbalize some of the challenges that your kids are having as they're trying to follow the conversation, right? And modeling is super, super important. We love how you are making connections to the podcast with what's happening in your classroom, but we love it even more when you tell us what you love and share the podcast with others. So I just checked recently, and there were 204, Pam.
Oh, nice.
Reviews. Yeah. So we would love it if you would continue to share with others and rate and review so that more people can find it.
Yeah, thank you. And thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com and keep spreading the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figureoutable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.